The grades have been updated. Make sure there's not a mistake in there, which happens. I had 2 mistakes in the last class, so verify it's not an error, and if there is an error, I apologize. I'll fix it. Test corrections, I would like to do them today, but this lesson doesn't really lend itself to a lot of time left over. It'll probably take about 35 minutes and then 2 sets of questions. So I think we'll do test corrections tomorrow because tomorrow's lesson is short. Okay. With that in mind then, first of all, would you fix my typo? We will not be finding the volume. We will be finding the volume. Although volume does sound really cool. Maybe Latin for volume. I don't know. Or just made that up. All right. You don't. Oh, you don't. You should ask. Would you please do that? Their algebra 1 level problem. It didn't give you the height, so assume the height is 1. Let's go with actually a little smaller. Let's go with the height is 1/2 inch. Not drawn to scale. Go. You should not need a calculator. My tool for the week. You don't go around using crutches when you don't need them, do you? Certainly not. Unless that works. Your copy's a little muddy, but that outer distance is 3/16. At least somebody listened. Are you working it out still, or you about to? 100. Yeah, actually, I had a ton of people. This made me really sad. What's half of 10/16? 5/16. Explain to somebody around you why it's not 5/8, which is what everybody, and I mean 3 people in the last class said. Why isn't half of 10/16 5/8? Because that's the same thing. 10/16 is 5/8. So did you really divide by 2, or did you divide both by 2, which really means you multiply by 1? So yeah, it's half of 10/16 is 5/16. That's so sad. And if that was you, then I would keep it to yourself and just be ashamed. Okay. So 1/4 minus 25, 256 times a half. What's the common denominator? 256. What is 4 times what? Or 4 into 256 is 64. 64 minus 25 is 39. 39, 256 times a half is 39 pi over 512. I suppose, no, it does not divide by 3. Okay, so it would be that, and the units in this case would be inches cubed. this really is the big idea of today. To get a washer, it's like taking an outer cylinder but taking away the inner cylinder that's not really there. But in calculus terms of setting up the integral well, you really want to avoid that and go straight to this. They both have a pi, they both have the same height, so you factor the pi and the h out, and it's really just a matter of the difference in the square radiuses, right? Or radii, right? Now let's talk. Oh, this is so much fun. Before we would take a region like this and revolve it. Now, if we revolve this around the y-axis, then we would get a figure like this. That is a solid figure, solid all the way through, right? And we would typically use y here. And we would find the volume by summing many cylinders. Or discs. We call them discs. Cool. Okay. Different today, though, is we're not going to go that region around x or y. We're going to go around x. Now, if I go to draw this, let's first draw the reflection. When I take this region and revolve it out the board and back to the opposite side, the reflection would look like that. Yeah? And then it would revolve back through the board and back up all the way. So when it revolved and it popped out of the board, this would come whoop. It would really, imagine coming out of the board would be this. What would it look like to you on the outside? Would it look funnelish to you? I mean, from the outside, what would it look like? It would look like a solid cylinder, right? It's only when you turned it and looked in that you would start to look like a funnel or a vase or something. Okay? So to the outside, it would look solid, but only when you turned and looked inside it would look like it had a hole. More important than that, more important than the figure is a slice. If you looked at some of these slices, when they got revolved, this slice would have a reflection of this, and when I joined it, it would look like that to the outside and that to the inside. And there'd be this huge hole in the middle. This one here would have the same outside, but it would have a little smaller inside, a little smaller region. I wish I would have stretched this a little wider. And then this guy would practically have no little gap in the middle. All said then, we're going to get mini washers, yeah? So the volume then is going to be the sum of many washers. And we just talked about how the washers are pi big R squared for the outer radius, take away the inner circle, which will be a smaller radius, and they have a common pi in each, so we can factor those out. Calculus then is infinitely many, infinitely small, or thin, to get the perfect volume. Instead of rectangles, we're getting smaller and smaller and smaller, so we get beautiful volume estimate by doing this. The height, if I go infinitely small, then the height of these, this here, will be starting to approach D, in this case. Okay. That's the big idea of washers. I would circle, in fact, the general idea is just D something, X or Y. We'll talk about Y in a second. But the height is a small difference. So let's get into the details. That's what makes every problem different. Right away, I just start by saying, here's the shell of the problem. You say in this case it's dx. Do you all agree? The height is, when I make, this is the height. I think you'll agree with that. When I'm going this way, am I not going horizontally a small distance? So because it's a horizontal distance, that's why it's dx, not dy. Big R. on all these, look at all these slices or all these cylinders. Here's the radius. The big R is the radius for the outside part. Is the radius for the outside part always the same, or is it varying? It's always the same, so it's constant. What's the big R? 4. Okay? Inner radius is the inner circle that we're taking away. Well, here the inner radius is here. Here the inner radius is here. Here the inner radius is here. Is the inner radius constant or varying? Varying. In every case, though, we're going from the axis up to the curve, so the inner radius is just the curve. Do I want to say the curve in x terms or y terms? X, because it's dx, I need to say the curve in x terms, and so it'll be x squared squared. Don't make that silly mistake that somebody always makes that says, oh, I can just write x because it's already got a square. No, it needs both. It's the curve squared, so x squared squared. The limits, are they 0 to 4? No, because we're dealing with x, they should be the limits of x, so they are 0 to 2. Most of the day we'll be doing without a calculator, but today we're going to do this, or this problem we're going to do without a calculator. What's the antiderivative of 16?
16.
What's the antiderivative of x to the 4th?
1/5 x to the 5th.
Okay. What is 16 times 2? What is 2 to the 5th? What is the common denominator? 5. So 32 becomes 160 minus 32 fifths. So our answer is 128 pi over 5. I gotta say, I often ask them, should I teach them the AP style or what I consider good math? You know, and sometimes those aren't the same. For example, AP style sometimes says you don't even have to simplify this. On the AP test, if you left it here, you'd be good to go. That to me is an abomination. That's ridiculous. You get an answer in that, man. That's the answer, not that. That's crazy. You can't add fractions. You can do all this calculus, but you can't subtract 2 fractions? Come on. Okay? I will say this, though. In terms of the AP grading, this is a pretty common free response. In Part A, you do area. Part B, you do volume. Part C, you do some other type of volume we haven't covered yet. They don't require units on these. So if you left no units, then you'd be fine. But if you do use units and you give them wrong, like you confused area with volume, then they will count up. So strategy being what it is, you have nothing to gain and stuff to lose from using units, so we're not going to use units. Okay? But what would the units be? It's volume. Units cubed. Okay. Will you try this one on your own? You'll find that some of these problems... Yes, I'm sorry. 0 to 2, because the limits of integration have to pertain to x, because x is our variable of integration, that's why 0 to 2. If it had been y, it'd be 0 to 4. Okay? Try this. I gotta say, the most common sources of errors are twofold. One is to forget the pi when you go to calculate. That is the most common error. People leave off pi. You type it in as you go. The second is people misidentify the region itself. Now that's super costly. I need to make something clear about carry-through error. Do you guys call it carry-through error, follow-through error? What do you call it? Carry-through error. Okay. Yes, AP grades for carry-through error with this caveat. If your error makes the problem and all its parts substantially easier, well, you don't get a benefit from being a nutbag. I'm sorry, you don't get to say, oh, I thought it was x instead of log base 2 of x. So everything is easy. You don't get a benefit from that. You're out on every part. Okay? If the assumption is that your error doesn't make it easier, or in some cases, many cases, makes it harder, then you're in. Okay? That said, on this, the most common error was people misidentify the region. It's so sad if you're going to do all this work and you're doing it with the wrong region. So I will say you're going to try this, but let's first make sure we have the region identified well together, then I'll leave you to the calculus. Give me something about log base 2. Give me some points, please. 0, 1 or 1, 0? 1, 0. What else? 2, 1. What else? Come on, more.
4, 2.
4, 2. There's another one we need. 8, 3. Okay? And obviously it has a vertical asymptote at the y-axis. Okay, that's the curve. Check. Y equals 1. What does that graph look like? Please go slowly and don't make it a horizontal when it's vertical or vice versa. Y equals 1 is horizontal. And x equals 8 is vertical. The region that's therefore enclosed by those graphs, not the x-axis, don't read it, it never said the x-axis, by those graphs is this quasi-triangular region in red. All right. Now, revolve that about the x-axis. You may use a calculator to evaluate the integral, but you should definitely show the whole setup on your paper. Ready? Answer? Not yet. Okay. Did you get something like 80-ish? Yeah?
88.
I got 80.1. Yes? Lejeune? All right. Let's compare our integral setups. The outer radius, is that, I have my outer radius in green. Is it varying or constant? Varying. The outer radius seems to be connected to the curve in this case. So the outer radius is the curve log base 2 of x, that quantity squared. Inner radius, which I have in black. The inner radius seems like it's always 1. The limits of integration, are they 1 to 8 or something else? 2 to 8. Because you don't start getting closure until you get to y equal 1, and when y equals 1, x must be 2, so it's 2 to 8. Next thing is when you put in your calculator, type pi right away. Don't say, oh, I'll type in the integral and I'll put pi in later. You won't. You'll forget the pi. Type in pi first, and then type in the integral. 80.103 ish was your answer. I think that's followed by an 8, so they would take 103 or 104 or more. You follow? Well, just like area can be x or y, volume can be x or y. So let's go to that idea here. Say you had the same region. Bless you. I'm going to stretch mine out a little. The same region like this, that's from 1, 2 to 8. But this time it's revolved around the y-axis. So reflect it and connect it. Now we know the log actually is not so steep as that, but I usually like to stretch my graph because otherwise your washers kind of get stacked too close together. So in terms of looking good, I like to stretch. Okay, so if I'm going around the y-axis, then let's make sure you understand the choices here. Any region can be divided up into rectangles, horizontally or vertically. Okay. Now, if I kept doing that kind of rectangle, then isn't the thickness dx-ish thick? Yeah. Okay. Now here's the problem with that. When you revolve that, students tend to think, I don't see any problem with that. That's a washer too. That's not a washer. Yeah, that's a really paper thin. It's not so much, I mean, have you seen a washer, a real washer, like cars and hardware kind of thing? It's flat and thick. This, what you're getting at that is more like this. Nobody would describe it.
Hello.
Nobody's going to describe that as a washer. Okay, this is a cylindrical shell. So the point is you don't want to go there. We are not there yet. You're going to want to do that later, but right now you're going to want, if it's around y, to use a y slice that's dy high. So that when that's revolved, that looks like a washer. Okay? So if it's around y, use y. The idea is still the same. The volume is pi, big R squared minus little r squared, times the height. But now the height, instead of being dx, is y. Now look at the outer radii for all these. Here's the outer radius. Here's the outer radius. Is that outer radius or those segments, are they always the same or varying? They're varying, okay? So it's obviously going to have a variable in it. It's really just the distance from the axis to the curve. So big R is the curve, but in x terms or y terms? Y terms this time. So what is in y terms? Y equals log base 2 of x in y terms is x equals 2 to the y. So big R is 2 to the y. Cool? For all these, little r, look at the little circles. Here's the little circles. The radius, the radius, the radius. On all those, the little radius is always the same. The little radius is constantly 2. Yeah, it's always 2. All right, and the limits of integration. What are they?
0 to 3. 1.
Y equals 1. Seems sneaky here. Do I have the right region here? No. This does not look like last class. Why doesn't it look like last class? Did I change this? No.
You're doing area somewhere above.
I'm getting ahead of myself and doing this. Sorry, I'm about to do your example for you. Sorry. So, why didn't you say anything? I don't know, I'm confused enough, man. I don't even know. I'm making it worse. I apologize. So, I was trying to exhibit how dangerous it is to misidentify the region. You just waste tons of time. See that? Do you understand now? Is my point made? Good job. Way to go, me. So here we go.
Can we just like switch the things?
No, we got to do it. So here's the curve. Y equals 1 is here, and x equals 8 is here. So, in other words, it's the same region. How can you screw up the region you just did 5 minutes ago? That boggles my mind. Okay? Do we all agree with that? Do you really agree? Okay. It looks like this then. Now then, the slice idea. If I slice this way, because we're around y, then to the outside, it would look almost solid. It would look like a cylinder to the outside, but there'd be this big concavity inside. Okay, so here I go. Pi big R squared minus little r squared. This time, height dx or dy? dy, okay. What is big R? If I look at big R, I trace over, I tend to make a big mess of my picture. Here's big R, here's big R, here's big R. All those blue segments, always the same or varying? Always the same. What's big R? 8. Little r, that's the little circles inside. Here's a little circle, here's a little circle, here's a little circle. Are those green segments always the same or varying? All right, so it's the distance from the axis to the curve in y terms. So now this is 2 to the y. All right. Limits of integration, are they 1 to 8? 1 to 3. Okay, 1 to 3 because in y, the upper and lower bounds of the region are vertical, so it's 1 to 3. You slap that in your calculator and be good. Try this one on your own to see if you're getting the idea with y. Those of you who are detail-oriented, I think you will enjoy drawing these graphs. Are you looking at that region? The region, don't start bringing, people start to look for the first enclosed region they can find. So I can't tell you how many people would say, oh, so that's the region. Why isn't that the region? Yeah, it has nothing to do with y equals 3. You're reading the x-axis is there. That's not part of the enclosure. So it's this. This is the region here. That's the region enclosed by the graphs there. You have something like that for a setup. Pi from 1 to, an integral from 1 to 3 of y squared squared minus 1 squared? Yes? Okay, any questions so far? Yes?
So is like whether or not it's dy or dx, is that just dependent on which axis it's revolving on?
Yes, it is. When it's around y, we'll use y for now, and when it's around x, we'll use x for now. It's the thickness of the slice. Okay, let's go on to two little wrinkles or little complications that are not too bad, and we will be done. Sometimes when you do areas, you get two areas. Sometimes then when you revolve two areas, you'll get two volumes, and you'll have to do two integrals. So consider the graph here. Y equals the square root of x is something like this. X equals 1 is something like this, and x equals 3, this. So it seems like
It's supposed to be y equals 3 to be the same as the last one.
x equals 3. Did I not include the x? I should be also the x-axis. Darn it. Sorry. And the x-axis. Did I forget? Yeah, no, and the x-axis. Darn it. Okay, so you're looking at this. Sort of trapezoidal region with me? All right. So if it's revolved around the y-axis, then the reflection would look something like it. One, x is 3. Okay. This is what I want. So if you revolve this, then you get something like this here shape. All right. So what's the complication? Well, look at that red region. If I were to draw slices, if I'm going around the y-axis, am I going to be using y or x kind of slices? Y. The y slices are this way because they have, I know it feels like that's horizontal, it should be x, but it's really the thickness that's dy. That's what makes the y slice, all right? Well, these, they're always the same outer and inner. But the minute you get up here, then you're talking about a totally different outer and inner, right? So because you have different big R, little r situations, you're going to need two integrals. You'll need to do one region. I'm going to do it in green here. One integral for when you revolve that lower region, and then another integral for when you revolve that upper region. You follow? Okay, so the lower region, pi big R squared minus little r squared, dx or dy here? Dy. All right, so for the lower region, look at all the radii. Big R, is it always the same or varying? Always the same. Big R is always the distance from the axis to the outer edge, which is 3. Inner R. When you do inner R, is the inner R always the same or varying? It's the same. Okay, so it's always 1. And what are the limits of integration on that part? Considering you're talking y, 0 to 1. Okay, that's the lower part. Now you could actually do that geometrically because that's not varying in any way. The second integral, pi, do the limits in a second. The second integral, what's big R now? When I do these slices, big R is here and here. So big R is constant or varying? Constant. Big R is always boom, 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 boom. Big R is always 3. I put an 8 there. I didn't need to do that. Big R is always 3. And little r. Here's little r, little r. Little r is varying, so it's the curve in x terms or y terms. Y, which means we'll use y squared. Limits of integration for the upper region. Careful. 1 to
3.
no, root 3. Okay, because if it's y equals x and the upper point is 3, then y is an x of 3, then the y is root 3. You see? All right. Then calculator, big time. Would you please pick up your calculator and throw that there pair of functions, f and g, into your calculator. And I'm going to clear this out. And functions. What was it? 4 sine squared, is that right? And what else? X minus 1 squared. Okay, you can adapt your window a little if you like. I like zoom box myself. Okay, you get something like that. Yes? No? This is not as, this I know most people think, oh, calculator ones are a gift, but there's a lot of places to mess up entries, so I hope you're trying this. It's not an automatic or a slam dunk. Okay, do you get that kind of situation? We? All right. Now, on the AP test, you would usually have graphs provided for you. And it's pretty common that you would, on your picture, do a little labeling because you're going to want to use these same points over and over again. And you want to have to keep writing them, so it's about time saving. If this is revolved around the x-axis, then what kind of slices should I use? Rectangles that go up and down or side to side? Yeah, it's dx slices, so they should go like that, yeah? You with me? All right, so that when I revolve this, good. Just to lay a foundation, let me throw one thing at you to lay the groundwork here. What if this were revolved around the y-axis? Okay. Now, typically we would use y for that, yes? Are you with me? Can you imagine why y would be terrible? Okay, it's varying. How many integrals would you need? 2. And here's the worst part. This, what's big R here? It's the distance from the axis to the sine curve, right? Okay, in y terms. And then what's the integral? Distance to the sine curve in y terms. So the integral would look something like sine curve squared minus sine curve squared, which is?
Nothing.
Yeah, nothing. Now the problem then is your arc sine is not forever, it's limited. So when you say arc sine, you would actually be only finding this part. To get this part of the equation, you would have to reflect that, negate it, to reflect it, and then shift it. Okay. So you would have a negated reflected inverse sine curve minus inverse sine curve. It's a freaking mess. It's terrible. Okay? So the point is you would never use y there. You would avoid y at all costs, which means you'd have to use an x slice. But if you use an x slice, you don't get a disk anymore. You get a shell. And so that's why the necessity for a second method. We'll talk about that later. But for now, let's go back to the question at hand. That's just meant to lay the groundwork. This is around x, so let's get into that. In order to do this value, what should I start with first in my calculator after I've drafted?
Find the intersection point.
Find the intersection points. Would you find the intersection points and store them? When I say store them, do you need to store x and y or just x? Just x. Why just x?
We're not using the y.
We're not using y as our variable of integration. We're using x. So store that x and find the other intersection point. What the heck? Okay. All right. Do you have something like I have 0.337 and 2.380? Okay. Okay. Like I said, on the AP test, this would typically be a multi-point problem. So you would probably on your work say, let x equal, what was it, 0.3 something? What was it? 38? 0.38 what?
338.
338, oh sorry, 0.338. Okay, and you might say, hey, I'm going to refer to that as a from now on in my work, okay? Then the readers will know anytime you refer to that, that's the reference. Also, I understand that your final answer has to be accurate to 3, but you understand that every part that they check has to be accurate to 3, including these? Okay, so you have to report 3 everywhere, not just your final answer. The other one is 2.3 something? 80. And I'm going to let the person know that that's going to be B. My integral then. Pi from A to B, which have been identified in my work clearly. Big R squared minus little r squared. Dx or dy? Dx. Also on the AP test and on my test, it is not required that you rewrite the whole function. And that's a huge time eater. If it has a name, use its name. F and G. You don't have to write the whole thing. What is big R? F, G, or something else? F. Big R is the distance from the axis to that curve, and that's the sinusoid. So it's F. Little r. It's the distance to the parabola, which is G. You punch that into your calculator. In order to get the practice, I do want you to do that. I told you the most common error is forgetting the pi, so type it in first. Pi. Shift plus A to B, maybe B. All right, here we go. Function, I think I have. Do I need another set of parentheses? Is this going to cut? I don't think it's going to write this, is it? Okay, put them in for me. Oh, thanks, what's that? X. Right there. All right. What'd you get? 53.998. As in area problems, what happens if you get a negative? You've done it wrong. Figure it out. It is not supposed to be in any case negative. You've made a mistake and it's negative. It's a positive value. Okay? Positive. Always. Okay. That's it. What do you think? You're good? Okay. Questions? Whatever we can get to on 78 and 79, I will answer them in the order you ask them. So, hit me. The keys to 78 and 79 are posted, by the way. If you have questions and I don't get to, they're on my website. On 78 or 79? 78, 17. Others, shout them out.
5, 79.
79, 5. 3, 79. 79, 3.
5.
78.5.
78.21.
78.21.
69.
70, which one, 6?
78.
78.
78.
78. Okay, here we go. We can maximize how much we can get through if you say, if you get specific, you tell me I didn't get this part, or I'm good at this point. If 7817, this is good because it requires little work, just a little vocabulary. F of x equals e to the x plus x. It says find the inverse implicitly. This requires two pieces of knowledge. First of all, how to find the inverse. You find the inverse by switching x and y. I don't know about Miss Kenna, but I'm pretty particular in that if it's not y, then you shouldn't be using y. If it's function, then I should be seeing this. X equals e to the f inverse plus f inverse. There's no y here. Now, your workaround would be, if you're a wuss, then you could say, let y equal, then there's a y there, and I'm okay with it. But you have to do that. I personally think this is its function notation, use function notation. Now the implicitly. If you know implicitly, then you say, woo-hoo, because implicitly means you are done. You don't have to solve for y. Implicit means mixed up is okay. You don't have to solve for. And so you are done. That's it. Implicitly, you're done. 79.5. 79.5 is wacky one. You've got this box or tank that's got a little gate at the bottom for the fish to get out or whatever. So where did you put your? This is 1. This is 1, and this is 5. Where did you put your origin? At the bottom of the box? Bottom of the box or bottom of the door? Bottom. I'm just gonna say here. Okay. Where's the top of the container then? 6. Now, the side to side of the container, I don't think ever pans out to be much. Is this force or work? Force. Force is row, depth, area. Now, this container is filled. So here's the top of the fluid. So what's the depth? 6 minus y. It's from the top of the fluid. Area, that's the area of these slices. The width of all those slices is 1. The height is the y. The only other thing is the limits of integration. 0 to 1 or 0 to 6? 1 to 6? That's the question. Okay. You're calculating the force where?
Against the door.
Against the door. So you should be limiting it to just where the door is, which is 0 to 1. Okay? And I don't know what the row is, but you can work that out. Okay, does that make sense? That was a weird one, I agree. 79.3, is that a question? Yes. Okay. 79.3, you've got this a rectangular tank, which they don't provide a picture for, but it's 2 deep, 4 wide, and 10 long. So it looks something like that. Yeah? Is it completely filled? Yes. It's filled with water. Oh, no. It's okay. This one's kind of funky. Find the work done in pumping enough water out of the tank to decrease the water by 1 meter. So the question usually is it 0 to 1 or is it 1 to 2? Imagine if this was the thing. Wouldn't this be filled? And so you're really, the first thing that gets removed is this is the first thing out, and this is the first thing out. So is it 0 to 1 or 1 to 2? It's 1 to 2. The top layer's got to go. It's not like you remove this and it just all drops down. It's 1 to 2. If you have other questions, I'll be happy to keep working this, or shall I keep going on this? Rho, distance, volume. So the distance should be 2 minus y. And the volume
I was like, you're really gonna
is constantly 4 by 10 by dy. Okay, hi. I can indeed. Sure, no problem. I need to pause this real quick. Hi, just a minute. Let me pause this before I